Hi everyone. We will now start our discussion on the cascode amplifiers. So just to quickly refresh what we did in the previous lectures, we discussed about a cascade of common source amplifiers and a cascade of n common gate amplifiers, and we drew the equivalent models. And we said that the problem with going for a cascade of common gate amplifiers was that the input resistance was very less. When you see it as an ideal transconductance amplifier model, the input resistance was 1 by Gm, okay, approximately 1 by Gm. And we also discussed that any BJT or a MOS amplifier circuit can be represented by an equivalent Norton circuit model, which is nothing but representing the circuit as far as the load is concerned. A MOS or a BJT amplifier, it can be a circuit comprising of a cascade of amplifier, MOS or BJT amplifier circuits. We can represent that as a Norton equivalent model with a short circuit transconductance Gm, which is measured by short circuiting the output node and applying the input and measuring the current flowing at the short circuited output node, and also by an equivalent output resistance R out, and that is measured by making the input go to 0 and then seeing the equivalent resistance as seen by the load resistance. Okay, and we said that the gain that one obtains by this model is simply equal to Gm times R out. That this is the unloaded or the maximum gain possible out of this structure. And we said there are two methods by which you can get a very high gain. We took two examples. One is a cascade of common gate amplifiers and the other one is a cascade of common source amplifiers. And we said in case of common source amplifier cascades, we said the R out was constant, it was always R naught, but we could actually increase the transconductance Gm. We could significantly increase it by cascading more and more stages. And similarly, we also said in case of a common gate cascade, okay, so we said that in case of a common gate cascade, we could actually keep the the Gm constant. Gm was just Gm. The short circuit transconductance was simply the same as the transconductance of every stage, but we could increase your output resistance significantly by adding more and more such stages. Okay, so then we just derived the small signal model for both, and we just compared. If you recall, this is the effective transconductance of a cascade of common gate amplifiers, and this is the effective transconductance of the cascade of common gate amplifiers that was just equal to the transconductance of a single stage amplifier. In case of a common source amplifier, it was much higher, but the output resistance was very, very high in case of a common gate cascade. And then we said we could replace the first stage by a common source amplifier. Then we said that was called referred to as a cascode configuration. Okay, we just replaced the first stage. So when we replace the first stage by a common source amplifier and then every other stage after that is a common gate, we said such a configuration we refer to it as a cascode amplifier. And for this architecture, for this cascode amplifier to give us a good gain, the load resistance, we said, should be always of the order of output resistance. It should be greater than the output resistance. Okay, see, otherwise the load resistance can significantly reduce the overall gain. Okay, we took an example where we assumed RL equals R naught, and we showed that in case of a common gate cascade, the gain was just reduced to a single stage gain, whereas in case of a common source cascade, we said that the gain was just reduced by half or 6 dB. Okay, so now this is what we discussed in the last class. We said mainly we discussed about the gain. We said there are two standard ways. One, either you increase the Gm keeping R out constant, or you increase your R out keeping Gm constant. Okay, and we finally derived a structure called the cascode amplifier, which gave us a very high input resistance, which combined the benefits of a cascade of common gate amplifiers. In addition to that, it also gives us a very high input impedance. So now we'll just talk a little bit about the cascode. Here I have shown the simplest cascode amplifier configuration, which is a cascade of common source, common gate amplifier, and here I've shown a common source cascade. Okay, Now the name cascode actually comes from, it actually dates back to the times when vacuum tubes were prevailing in the electronics industry. So vacuum tubes again had 3 terminals. So one was called the grid terminal. I'm not drawing the symbol accurately here. Okay, the other 2 terminals were called anode and cathode. The symbol is not accurate for a vacuum tube. I mean, okay, I'm just trying to make a point here. I'll just try to explain what I'm trying to say. So it had a grid terminal and anode and cathode. So if you recall, a vacuum tube essentially has a coil which is heated, and that coil acts as a cathode. So it is nothing but a coil which generates electrons, and we had another plate which was connected to a positive terminal called as anode, and this plate was called the cathode plate, and in between there was a terminal called the grid terminal. So this was the model for a vacuum tube amplifier. So by controlling voltage on the grid terminal, they could control the flow of electrons between cathode to anode. So by heating the coil we could generate electrons, and these electrons will be attracted to the positive plate, that is anode on the other side. And in between there was a plate, a metal plate introduced, which could actually control the flow of electrons between anode to cathode to anode. In a way, we are controlling the current between anode to cathode. That's the transconductance effect. A MOSFET also does the same thing. It's more of a field effect device. Okay. So what they did was that conventionally, when you want to get more amplification, we had to cascade stages. So they would cascade the anode of one stage to the grid of the other stage. So the anode of one stage would conventionally go to the grid of the other stage. But then they realized that by connecting the anode back to cathode and using an anode as the other output, the anode of the next stage as the output, they could actually get wideband amplification. The gain was constant for a larger range of frequencies. In fact, when we discuss the frequency response, we'll discuss that in case of a cascade of common source cascade, there is something called Miller effect, which reduces the bandwidth of the amplifier. Okay, that Miller effect was not there in a cascode configuration. I mean, in the cascade of when they do a cascading like this, wherein they take the anode, instead of connecting it to the grid, they could connect it to the cathode terminal. So this is like equivalent to, you can see what I've done is I've taken the drain and connected it to the gate of the next stage. So that's essentially a common gate configuration. Okay, so that's why it was a cascade of anode and cathode. So there is an anode and a cathode, so that's why cascade and ode, the word ode comes from that. Okay, so they just join the 2 words and you get that. So that's just to distinguish the cascade of the regular cascade of the common source or anode going to the grid. So just to distinguish that, the name was thought. There is also other explanation where there was a device called pentode, which had a very similar structure to this. Okay, from there, that's a big complicated name, how the cascode actually arrived. The name cascode was originated. Okay, you can read up about that, about pentode, and you can see how the name cascode came from that. Okay, so the idea was essentially this: when you go to frequency response, we'll see what is the advantage that we are going to get in terms of the bandwidth. Okay, so now like we did in the for all the previous cases of amplifiers, so whenever we discussed amplifiers, we discussed 3 important parameters, so which is gain, the unloaded gain, R out and R in. So similarly, we will compute all the 3 parameters for a cascode amplifier as well. Okay, so first what I've shown here is a generalized cascode amplifier. The first stage is common source and every other stage is common gate. We just stacked many common gate devices, you get a cascode configuration. But conventionally, the more popularly used ones is just 2 stages, which will be just a common source and common gate cascode. Okay, but we can generalize this by stacking more and more common gate devices. So again, the procedure remains the same. We'll have to find the output resistance seen at the drain of the nth device here. Okay, and we are making the input to go to 0. And similarly, we'll have to find the short circuit transconductance by shorting the output node here. And we discussed to find the short circuit transconductance, when we apply voltage Vi here, you have a current Gm times Vi flowing here. Now if you recall, there is a resistance R0 here, and you have to just find what is the resistance seen at this terminal. If you recall from the previous lecture, I said for a common gate configuration, if you ground the drain, the resistance seen here will approximately be 1 by Gm. And if you take a common gate configuration, the input resistance is actually a strong function of what you connect at the load. If the load resistance is small, I mean 1 by Gm, when I say small, it is small compared to R0. It should be small compared to R0. Then you can approximate your input resistance approximately to 1 by Gm. So that's the criterion. The load resistance we connect here should be much smaller compared to R0. And which is true here. 1 by Gm is actually much smaller compared to R0, which is almost intrinsic gain times smaller. Okay. So using that, I'm going to say that if I'm connecting 1 by Gm here, the next stage will also offer a resistance of 1 by Gm and so on till finally I'm going to come to this stage. This will also offer a resistance of 1 by Gm. Okay, at every stage I'll see 1 by Gm, 1 by Gm and so on. So now the current has to split between 1 by Gm and R0. So if you can very easily find out the current that is going up into the device will be Gm R0 by 1 plus Gm R0. Okay, it's just a simple potential current division, and that I can approximate it to 1. And that same current, because it's just a common gate amplifier as a unit current gain, so you feed some current into the common gate amplifier, you will get the same current at the output as well. So you have fed some current II here, I0 will be exactly be equal to II, even the presence of R0. Okay, so now at every stage the current will be the same, and finally Gm will simply be equal to in this case the Gm will be minus Gm. It will be Gm of a single device. Transconductance of, in fact, it's the transconductance of the first device. To be very, very precise, it's actually the transconductance of the first device. Okay, the other devices can have different transconductances. The short circuit transconductance will depend upon the transconductance of the first device. But in all the previous examples, we have analyzed all the devices are identical with same transconductances. Okay, so that will be the output short circuit transconductance will just be Gm itself. Now what about the output resistance? If you recall from a cascade of common gate amplifiers, it's very similar now. The structure is very similar. First, I'll assume just you have one device. If you have one device, if you recall, the resistance connected to the drain to source is R0 here. Then the resistance seen here, the first drain, the drain of the second device will be Gm R0 times R0. So it's going to be Gm R0. It's actually, if you recall the exact expression, it's going to be, if this, let's say this is R0 dash or something like that. Let me just call it R0 itself. So if this one here is R0, so it's going to be R0 into 1 plus Gm R0 times R0. Okay, so here again, when we are approximating this result, as long as this R0, the resistance, you can actually treat this device as a source degenerated device and with a degenerating resistance given by R0. Okay, then you can approximate this resistance. R0 is a large enough resistor, so you can ignore the R0 here. Okay, in the expression, in the final expression, you can simply say that it's actually going to be simply R0 into 1 plus Gm R0. So I'm going to ignore 1 as well. So it will be R0 into Gm R0. So the gain R0 gets multiplied by the intrinsic gain. Okay. Now, when should we ignore this resistance? There is also another term which is R0. So normally, if you recall from the old lectures, I discussed how do you find the actual reflected impedance seen. Let's say this is Rs and you want to find the resistance seen at the drain. It's actually Rs plus 1 by Gm parallel R0. The whole thing getting multiplied by 1 plus Gm R0. So that's what is the actual expression. Okay. So whenever so when you see this expression here, your Rs has to be compared with 1 by Gm. So if your source resistance is greater than 1 by Gm, then you can apply this result, apply this approximation directly. I can ignore what is connected. I can ignore the impedance contributed by this device. Okay, so that I can ignore it. So what you connect at the source, if it is greater than 1 by Gm. So here it is R0, so which is obviously intrinsic gain times larger than 1 by Gm. So I can ignore it, ignore this device contribution altogether. So you can simply say the output resistance is simply the intrinsic gain of this device times this R0. Okay. So you can write it as Gm R0 times R0. So when you add two such devices, then you will have to find the resistance here first. That will act as a source resistance for this device. This here is going to be GM R0 times R0. So that is A times R0. So this will be A times R0. So the resistance seen here is going to be A square times R0. And so on. So we have done this in the last class as well. So if I have n such devices, so here it's 3 devices, I get A square R0. When I cascade n such devices, I am going to get A power n minus 1 times R0. Okay. So I just probably, I just spent a little time just explaining this a little bit in detail. If you just go through that, you will understand it's very, very simple. Maybe you might have felt it's a little complicated what I presented there, but it's not really. You just go through the source degenerated MOS amplifier, when to make this approximation. So I said simply A times whatever you connected, A times RS. A is the intrinsic gain of the source degenerated amplifier, okay, times RS will be your output resistance. When can you apply this? You can apply this approximation if your RS is much greater than 1 by GM. That's it. And that holds true here. So that's why directly multiplied by A times R0. Okay. Yeah. So finally we have a model, a small signal model, an equivalent model for a cascade amplifier, a cascode amplifier. Okay. So here if you see the input resistance is infinity because your input resistance is seen into the gate. So your Rn is actually infinity here, and Rout is very high. It's significantly high. It's exponentially higher compared to a single stage amplifier. It's A power n minus 1 times R0, and GM, the transconductance, is simply the transconductance of the first device, very close to the transconductance of the first device, and I've assumed all the devices are identical, so it is simply GM of any of the devices. So the unloaded gain is simply GM R0 whole power n. Okay, so that's simply A power n, where A is GM into R0. Okay, so that's it about cascode of MOS amplifiers. So I think now we have already discussed a little bit about bipolar junction transistors as well, BJT amplifiers as well. So I thought there is some very interesting results as far as BJT amplifiers are concerned, cascode amplifiers are concerned. So which is what I thought I'll discuss it here as well. So in a similar way, if you want to go for a cascode configuration in a BJT, you will have to cascade a common emitter amplifier, and then after that you will have to cascade several common base amplifiers. So that's the way you get cascode configuration. Now if you look at the MOS based cascode amplifier, I said that the intrinsic gain, the maximum gain that you can get out of, the unloaded gain is A power n, where n is the number of stages. So if I just keep increasing n, as of now I don't worry, I don't care about the supply voltage problem now. Okay, let's say I can accommodate to stack as many devices as I can theoretically. If n tends to infinity, then I could get really large gains. The gain will also tend to infinity. Okay, that's because if you see here, the GM remains the same. It's independent of the number of stages, but the Rout actually keeps increasing exponentially, or Rout becomes infinity. Okay, that's what happens. But in a bipolar junction transistor, what happens here, we'll try to find out what happens to the expression for Rout. Is there any limiting value for Rout? So that's what we'll see here. Now, in case of a simple emitter degenerated BJT amplifier, so if you recall, we said that it's not the same as a MOSFET because there is an R pi present between base and emitter. Okay, so that R pi, if you recall, it's going to limit your output resistance. So the output resistance of this stage, it's going to be 1 plus GM R0 times the R0 here, and R pi will come in parallel, R0 in parallel with R pi. So you're always going to get an R pi in parallel with R0. Okay, so even here I'm going to have an R pi here that will come in parallel with whatever resistance I see here. So eventually, let's say I keep cascading infinite such stages, so I'm going to ignore the stages beneath this. So if I just want to find out, I'm just completely open circuiting the emitter itself. Okay, I'm just open circuiting the emitter. If you just open circuit the source of a MOSFET, if you recall, the resistance seen at the drain is simply infinity because there is no current that's going to flow. If you have grounded the gate, source is open, drain is open, the resistance seen at the drain will be infinity. Okay, but that's not the case here. In a BJT, on the other hand, if you open circuit the emitter, there is still a resistance R pi connecting from emitter to ground. Now that will get multiplied by gm r naught. So it will be r pi into gm r naught. So which will again be beta times r naught. So this is the fundamental limit of output resistance that you can get out of a bipolar junction cascode configuration. Okay, you cannot exceed beta times r naught. So it is actually independent of the number of stages. So initially it will have a dependence on the number of stages. After some time it will become independent of the number of stages. It will just be simply be equal to beta times r naught. Okay, and so similarly the maximum gain because of which will be limited to beta times, the gm is still the gm, the short circuit transconductance will simply be gm times beta times r naught will be the maximum possible gain with the minus sign. The minus sign comes because of the first stage being common emitter. Okay, so that will be beta times gm r naught. Okay, so this is the fundamental limit in gain you can get in a bipolar junction cascode amplifier. Okay, so this is the limitation in a BJT amplifier. In a MOS amplifier, the advantage is you don't have a beta. Beta, you can see it as a MOS amplifier as a device with infinite beta, infinite current gain. So finally, in this lecture, we will just analyze one special case. What happens when RL equals R naught for a cascode amplifier. So we already did this analysis. We can directly go for the small signal model. If you recall, if you just see what we did a few moments ago, we said that we can draw an equivalent Norton model for the output. So this is a power n minus 1 times R naught. Okay, and if I just connect this a load resistance of value, if I just connected a load resistance here of value R naught, okay, if I just connected a load resistance of value R naught is going to be much smaller than a power n minus 1 times R naught. So I can ignore this resistance altogether and the gain will simply reduce to gm R naught. So that we are aware of it with a minus gm R naught. So that's, if you load the output stage with a resistance equal to R naught, the gain, the DC gain is simply going to reduce to the gain of a single stage, which is minus gm R naught. But we'll just try to see what happens in each and every stage, because we have n such stages. What exactly happened? Where did we lose all that gain? Okay, here in the model, of course, it says that the load resistance is much smaller than output resistance, so you lost all the gain. From the model, we definitely have an understanding for that. But where exactly do we lose? And you have n such stages. What happens to the gain of the individual stages? Okay. Now to analyze that, what we need to do is first we'll have to find the impedance at every node. Okay. So first, I'll start from the last device. So this is the nth device here, as shown here. It's a common gate configuration. You are loaded that the RL is R naught. The load resistance is R naught. So if you are finding the input resistance for the common gate configuration, that's going to be 2 by GM. So it's, I'll just write the result. It is RL plus R naught divided by 1 plus GM R naught, which I said can be approximated to 1 by GM plus RL getting divided by the intrinsic gain. RL divided by GM R naught approximately. Okay, so RL is R naught, so you get 1 by GM plus 1 by GM, so you get 2 by GM. The stage after that, we'll see a resistance of just 1 by GM. So if you see what we discussed a few moments ago, I said if the load resistance is actually smaller than, here the load resistance has to be comparable to R naught. If it is smaller than R naught, then we can ignore it. We can just approximate the input resistance to 1 by GM. Okay. Now for the first stage, I'm just coming from the nth stage. It's at the source terminal of the nth stage, it's 2 by GM. At the n minus 1th stage, this will not matter because it's smaller than R naught. So the input resistance will simply be 1 by GM. And so on and so on. At every stage after that, we'll simply have a resistance of 1 by GM. Every stage. Okay. So now if you are to find the stage gain of the first stage gain is going to be GM into GM, which will be minus 1. GM minus GM into 1 by GM, so it will be minus 1. Okay. We lose the gain in the first stage. And every other stage, because the current is going to be GM, but the impedance seen at every terminal is going to be 1 by GM. 1 by GM. Till n minus 2 stages, we are going to see a gain of, the magnitude is going to be 1 for all the other stages, because see, for example, if I have a common gate amplifier with a resistance of 1 by GM connected this way, I have a current GMVI entering this, so the same current will flow through this and you will get a gain of 1. So every common gate will see a gain of 1. Okay, n minus 2 stages, till the n minus 2 stage. Now the last but one stage sees a resistance of value 2 by GM here. So this is n minus 1th stage. So the current entering is GM Vi. The gain will simply be for this stage will be 2. Okay, the gain for the last but one stage will be 2. And the last stage will see a load resistance of R0. So here you can say that 2 Vi appears here. So the gain is I'll say minus 2 Vi. The first stage offers a gain of minus Vi and so on till the n minus 2 stage the gain is 1. So you will get a voltage of minus Vi. At the n minus 1th stage output I am going to get minus 2 Vi. And finally at the last output, so if you again if you just refresh your memory as to what we did for common gate amplifiers, if you terminated, the output resistance of this amplifier is R0. If I am driving it with a voltage source at this point, output resistance is R0. So intrinsic gain is 1 plus GM R0 and output resistance is R0, load is R0, so you get a factor of half here. Okay, so that 1 plus GM R0 by 2 into 2 will be 1 plus GM R0, which is approximately equal to GM R0 itself. So the total gain, there is a minus sign here, is simply minus GM R0. Okay, so we are going to lose every stage is it's going to offer a gain of 1 except the last two stages. The last two common gate stages, are going to offer us a gain of, so the last but one, so this is n minus 1th stage and this is nth stage. So this will offer a gain of 2 and this will offer a gain of GM R0 by 2. This stage, if you terminate it with R0. Okay, every other stage is going to give minus 1. The first stage will give you minus 1 and every other stage will give a gain of 1, 1, 1 and so on. Okay, so that's it about the analysis of the cascode amplifiers. So finally, like I did for every other single stage amplifiers, so we discussed about a test bench to measure the intrinsic gain. Okay, so here I've shown a test bench which can actually measure the unloaded gain of a cascode amplifier. Okay, so we have two cascode amplifiers here. So the gate current, so here we have already discussed why we need to connect a resistance between drain and gate. Okay, so that will ensure that so when you bias a device, all the three terminals should be biased. The drain, the gate and the source should be at fixed DC potentials. Okay, the DC voltages should be fixed, or you should at least define the VDS and VGS has to be defined. Okay, now this way of connecting a resistance RB between gate and drain ensures that VDS equals VGS for both the devices. So I'll assume this is 2, this is 1. So VDS2 will be equal to VGS2 and VDS1 will be equal to VGS1. Okay, so there is no DC current flowing through RB, so the voltage potential drop, DC potential drop across RB will be 0. So this node, the voltage at this node, the DC potential here will be simply equal to VGS1 plus VGS2. So you can, by now you should be able to see that. It's very simple to see that. Okay, so using this test bench, I have connected a large capacitor here at the gate of the second device. So that's because we have to be able to see a cascode action, which means second stage has to be a common gate amplifier. So the gate for ACs, for the frequencies that we are trying to find, the frequencies of interest, this gate should look like an AC ground. Okay, so if you see this R and C is like a low pass filter. So 1 by RBC will be like a pole. Okay, 2 pi RBC. You can choose your capacitance such that, I mean, if you're running an AC analysis for 100 Hertz or 1 kilohertz and so on, you should ensure that this pole falls before that. This pole occurs much before that. Okay, so then when you're running the AC analysis, this capacitor will ensure that the second device is, if I'm going to draw an AC circuit model for this, it should look like this. Okay, this capacitor will be like a short circuit and VI is applied as it is, and that's it. So it will just reduce to this circuit, what we have shown here. Okay, RB can be ignored. Again, you have to choose your RB much greater than R0. Okay, in fact, you should choose your RB, in fact, even greater than intrinsic gain times R0 for this test bench, where A0 is GM R0. Okay, it should be large enough for your simulations. Okay, so here we have forced the VDS to be equal to VGS. Again, you can have a programmability on VDSs as well. Individually, we can tweak the VDSs. So here, I have already discussed this test bench for a common source amplifier. So you can follow a similar approach here as well. For example, the VDS1 for this device VDS1 is going to be VB plus VGS1. So let me call this as VB1 and VB2. So similarly, VDS2 is going to be VB2 plus VGS2. Okay, so now by varying VB1, so this is VB1 here. So by varying VB1 and VB2, you can have the simulations for different values of VDS and VGS. Okay, and you can simulate the AC, do an AC analysis and simulate the gain. And the choice of this coupling capacitor CC, if you see the looking impedance when you are seeing here, since I have connected one resistor RB here, you can actually show that the resistance will be approximately very close to be equal to 1 by GM. Okay, that can be easily shown. But I'm not going to do that. So we have already derived some problems like that. So the pole that this at the input you are going to form, this will behave like a high pass filter. At the input it will behave like you have a capacitor CC and a resistance of value 1 by GM, and so you should choose this pole. So this will be GM by 2 pi CC. Again, this pole should also be far before it should occur way before the simulation frequencies of interest. Okay, so such that for the frequencies of interest, so this is a high pass filter with a characteristic like this. The pole I am drawing the magnitude response is going to occur at GM by 2 pi CC with a gain of 1 after the pole. Okay, so you should ensure that you should be simulating in this frequency range where this capacitor acts like a short circuit. Okay, most of your input signal appears at the gate of this device. So that's it about single stage cascode amplifiers. The next class I'll discuss a few problems on cascode amplifiers.